Hello everyone, and thanks for watching Edupedia World Videos. In this video we'll start the new chapter, Specific Heat Capacities of Gases, and we'll also look in detail at 4 specific types of processes. We've seen two different definitions for heat capacity of a gas. One is related to the mass, which comes from the equation Q is equal to ms, or rather let's write it in the differential form now, dq is equal to ms dt, which says that S is equal to 1 by m dq by dt, or dq is equal to n c dt, where n is the number of moles, which means C, this is the specific heat capacity, this is the molar heat capacity, is 1 by n dq by dt. Specific heat capacity. Now when we are talking about gases, it's easier to talk in terms of number of moles, so we'll be using the second one more often. Now, there are many different types of processes, and dq does not change with dt in the same way in every process. That is, dq by dt is not the same in every process. There are two specific types of processes for which C is specifically defined as a different name. Cv is defined as 1 by n dq by dt, and we write it like this, bracket V. This denotes that V is a constant. So Cv is 1 by n dq by dt when the volume of the system is constant. We are specifically talking about gases, so the volume of the gas is constant, and this is called molar heat capacity. I'm just going to write MHC for short. Molar heat capacity at constant volume. And of course, this will be the molar heat capacity of a process if the process is isochoric. That means if in the process the volume of the gas is not changing. Then there is Cp, which is 1 by n dq by dt at constant pressure, and that is called the molar heat capacity. Molar heat capacity at constant pressure. And of course, this will be the heat capacity of the process if the process is isobaric, or if in the process the pressure is constant. Pressure is constant can be accomplished in many ways. One of the ways is if you have a piston attached to the gas, movable piston. So as the gas heats up, let's say the volume increases, so this piston will go up. Because this piston has to stay in equilibrium, the pressure of this particular gas has to stay same as the pressure due to the mass of this piston plus this atmospheric pressure, and that of course is a constant. So when you put a piston on top or on the side of a container, the pressure inside that container is constant because that is adjusted by the moving of the piston. Now, the two most important formulas in this chapter are the two formulas you've already studied. One is PV is equal to nRT, the ideal gas equation. The other is dQ is equal to du plus dW, the first law of thermodynamics. And these are the only two equations that will be needed in this chapter, and everything else will be derived from them. So first of all, let's derive a few standard results. Let's talk about the cases where the pressure is constant and the volume is constant. So this equation can be written in terms of its differential components as dq can be written as nc dt is equal to du plus dw can be written as pdv. We saw this in the last video. Now dq is nc dt for any process, and c keeps changing with processes. C will be Cv if the process is isochoric, it will be Cp if the process is isobaric, it will be some other C if the process is different, right? So this is the general equation. Now what happens when dV is 0? If dV is 0, that means the process is isochoric. In that case, this term will be 0, the work done by the gas will be 0, and the equation we get is NC dt, except in this case, since it's an isochoric process, we'll use CV, the molar heat capacity at constant volume. This is equal to du. Right? Now, there's an interesting point now. We talked about path variables and state variables in the last class, and we said that state variables are those which do not depend on the process, they just depend on the initial and final conditions. So, internal energy was a state variable. That means if you go from, let's say this is the PV diagram, if you take a gas from point A to point B and you take it through many different processes, du will be the same in all of those processes, because du has a particular value at this point and a particular value at this point. So the change in u will be the difference of those 2 points regardless of how we went through, how the process was taken. But dw and dq are path variables, so they do depend on the process. So from this equation, one result which we can derive is du is equal to ncv dt always. Not just in an isochoric process, but in an isobaric process or in an adiabatic process or in any other process. Since the change in internal energy does not depend on which process is occurring, and we know that for the isochoric process it is ncv dt, that means for every process it is ncv dt. So we can replace this equation. This was the general equation, and the general equation now always becomes nc dt is equal to ncv dt plus P dV. NCV dt is du always, not just in one particular type of process, but always. Right. Now let's consider, we saw dV is equal to 0. What if pressure is constant? That is, it's an isobaric process. In that case, if we look at the second equation, I told you these are the 2 equations that will be used. So we use this one, now we look at this one. If the pressure is constant, okay, even if the pressure is not constant, what is the differential form of this equation? That would be V times dP plus P times dV. I am using the product rule for differentiation, is equal to, generally we'll assume that the number of moles will be constant. That means the amount of gas is constant. We are not taking out or putting in any gas. So nR dt. Now when the pressure is constant, the process is isobaric, then V dP will be 0. Or you could have directly seen that from here, differentiating, if P is a constant, we just take it outside, and the derivative of PV with respect to the volume will be P dV. Right? So P dV can be written as nR dt, only for isobaric processes. Now, this chapter overall is very easy, but these small things you need to remember. Actually, not remember, that's the wrong way of doing it. You really need to understand how this occurs. So I'm just telling you one thing which you need to remember always. These are the 2 equations from which everything comes. And if you know how everything is derived from these 2 equations, then you don't really need to remember a lot of stuff, because it takes 5 seconds to derive it. Right? If you know PV is equal to nRT, it will take 5 seconds to derive that for an isobaric process, P dV can be nR dt, because V dP is 0. So for an isobaric process, NC dt. Now for an isobaric process, C will be Cp, right, molar heat capacity at constant pressure. That is equal to NCV dt plus P dV can be written as nR dt. This gives me a very important relation, Cp is equal to Cv plus R, or Cp minus Cv is equal to R. Right. So the difference between molar heat capacity at constant pressure and constant volume is a universal constant whose value is equal to 8.314 in standard SI units. I don't exactly remember what the units are. Right. So this is one important equation. The other important equation is just, it's basically a definition, not an equation. It's the definition of gamma. It is the ratio of the 2 heat capacities, Cp and Cv. Right, and it has a lot of other significances. That's why we've defined it separately, but it is nothing but the ratio of Cp and Cv, and it is different for different gases. So now one small thing left. What if we know gamma? Can we calculate Cp and Cv? So we know Cp by Cv is equal to gamma, and we know Cp minus Cv is equal to R. Right, R is a constant, gamma depends on the gas. It will have a particular value for nitrogen, a particular value for oxygen, and so on. We'll talk about it in more detail at the end of this lecture. Now, using these two equations at two variables, you can substitute one into the other, and you'll be able to solve and get that Cp is gamma R by gamma minus 1, and Cv is R by gamma minus 1. Right, so you see Cp minus Cv is R and Cp by Cv is gamma. So if you know the gamma value of a gas, you know both Cp and Cv of a gas, because R is a universal gas constant. Right. Now let's look in detail at the four different processes we talked about. The first process was the isothermal process. And I'll draw the PV diagram for all of these, but from the PV diagram it's pretty easy using PV is equal to nRT to draw the VT diagram or the PT diagram and so on. So PV diagram, we have the equation PV is equal to nRT. Differentiating it, we get PdV plus VdP is equal to nR dt, right, which came from PV is equal to nRT. Now in an isothermal process, T is equal to constant, and of course we'll assume the number of moles to be constant. That means the equation for an isothermal process, every process has a specific equation. The isothermal process equation is PV is equal to constant, right, and the equation for PV is equal to constant is a hyperbola, and it goes like this. Let's say in this direction. So as the volume is increasing, the pressure is decreasing. Right. What is the slope of this curve? So this is the PV curve, so which says that PdV plus VdP is equal to 0 in this case, because dt is 0. So that gives me dP by dV is equal to minus P by V. So that is the slope of this curve. That will be important when we compare it to other curves. So the slope of this curve at any point is minus P by V. So at this point we have a small value of V and a high value of P, so it's a high negative value, and it keeps changing. At any point the slope will be given by minus P by V. Right. Let's try to calculate the other important quantities, dq, du and dw. So du we know is always NCV dt. That means in this case du is 0. Right. We need to find out what dq and dw are. So dw is always pdv. That means w is always integral of pdv. Right. Now we can't integrate it directly because neither p or v are constant. But what is constant is t. So I can use this equation to eliminate one of these, and I can write it as integral of dv times P can be written as nRT by V, right? So this becomes the integral of nRT dV by V from V1 to V2. Let's say we are going from initially V1 and P1 to V2 and P2, right? So from V1 to V2, that is nRT ln V2 by V1. So that is the total work done if I take a gas from volume 1 to volume 2 through an isothermal process. And we know that delta Q is equal to delta U plus delta W. Delta U is 0. So the heat given will also be nRT ln V2 by V1. So a certain amount of heat is given to the gas. All the heat goes into work done. None of the heat raises the internal energy of the gas. We talked about how isothermal processes occur very, very slowly. If I have this gas and it is kept in a temperature, then if I change the properties of the gas, at every point it will have enough time to communicate heat with the surroundings and get back to its original temperature. Finally, we'll talk about C for every process. C is 1 by n dq by dt. So in this case the value of C is infinite. You'll need an infinite amount of heat to change the temperature even slightly, because actually the temperature isn't changing at all. Right. By the way, this PV is equal to constant. This is what we talked about earlier and named it as equation of state. Right. It could also be T is equal to constant. P, V and T are the properties of state, and the equation relating to that is called the equation of state. The things we covered for isothermal, those are the exact things I'll cover for the other three processes as well. So the next process is isochoric. Isochoric means volume is equal to constant, and this can be taken as the equation of state, that V is equal to constant. What will the PV curve look like? It will simply be like this. The pressure changes from P1 to P2, the volume stays V1, and V1 is equal to V2 is the same if you want to call it V2 as well. Right? What is the slope? The slope is infinite. Right. What is delta W? That is 0, because it's an isochoric process. What is delta U? That is always exactly the same, that is NCV dt becomes delta T, so NCV into T2 minus T1. This is always the case, right? Delta U is the same always. So since delta W is 0, delta Q also becomes NCV T2 minus T1. By the way, I'm going to randomly shuffle between writing delta U and du. If I write du, this has to be dt. So I'll be consistent on the LHS and RHS, but both the equations are the same. One equation is just the integral of the other equation. And obviously we know from this equation or directly that C in this case is CV. Right. So yeah, that's easy enough. I think we've covered everything for this one. Let's look at the next one. It's an isobaric process. In an isobaric process, P is a constant. That can be taken as the equation of state. The graph would go something like this. If it is going from V1 to V2 at a particular value P or P1 or P2. Right. Delta U, as always, will be NCV T2 minus T1. We are going from P1 V1 T1 to P2 V2 T2 always, right? So in this case, delta U is equal to NCV T2 minus T1. Delta W will be equal to P delta V, this area. But since P is a constant, P delta V can be written as NR delta T, right? P delta V is equal to NR delta T. This is not always true, but this is true if P is the same in both cases. Otherwise, this would be delta of PV, change in PV. Right. So this is equal to NR T2 minus T1. So adding these two, we get delta Q is equal to CV plus R T2 minus T1. And we can see from this or directly that the heat capacity is Cp, which is equal to Cv plus R. We proved it earlier, now we've proved it again. Right, sorry, Cv plus R. The slope in this case is 0 of this graph. The final and in my opinion the most important is the adiabatic process. Okay, just a word about when these processes occur. Isothermal processes occur very slowly. Isochoric processes occur when we have a fixed container. Isobaric processes occur when we have a piston on top of a container which can move. And adiabatic processes occur very fast because the system does not have any time to exchange heat with the surroundings. So delta Q will be 0. So in an adiabatic process, delta Q is equal to 0. Is that the equation of state? No, the equation of state relates P, V and T. So we'll derive the equation of state. Right, let's see how it's done. What is delta U? We know that is NCV T2 minus T1. Right, we can't yet draw the curve because PV curve because we don't know the equation of state. We will be deriving it. Right, let's say this from this point to this point. right? So delta W will be the negative of this value, because we know that their sum delta Q is equal to 0, right? It's better to write it in the differential form now. So du is ncv dt and dw is pdv, which is minus nc dt. So we know pv is equal to nRT. That gives us pdv plus vdp is equal to nr dt. So that basically gives us n dt. We divide this by r, that is n dt. I'll substitute n dt here. This is cv. So that I'll get dv and dp, and I'll calculate the relation between p and v. So this gives me p dv is equal to minus cv times p dv plus v dp by r. Right, let's take r to this side. And what we get is r p dv plus cv p dv. So that is cp p dv is equal to minus v cv dp, right? So I apologize for the weird way I'm using my space. So that gives me cp by cv is gamma, so that gives me gamma dv by v is equal to minus dp by p, right? You can integrate both sides and you get minus ln p2 by p1 is equal to gamma ln v2 by v1, or you can write this as ln p1 by p2, and you can remove the minus sign, and this becomes this to the power gamma. So what we get is p1 v1 to the power gamma is equal to p2 v2 to the power gamma, and this is true for any 1 and 2. So the equation of state for an adiabatic process is pv to the power gamma is a constant, right? Pv is a constant was for isothermal, pv to the power gamma is a constant is for adiabatic, right? And if you try to draw the graph, it looks like an isothermal graph with one difference, and this is important because very often by looking at the graph you'll need to differentiate between whether it's isothermal or adiabatic, because they look quite similar. And now the slope comes into play. M in this case will be dp by dv, right? If pv to the power gamma is constant, that means dp times v to the power gamma plus p times gamma times v to the power gamma minus 1 dv is 0, right? If you calculate dp by dv from this, what you'll get is it is minus gamma p by v. Whereas if gamma was 1, that means pv is equal to constant, it would have been minus p by v. So the difference between the two is the adiabatic is steeper, it has a greater magnitude of slope. So if you have two curves like this, then this is isothermal and this is adiabatic. So the way to remember it, either you can just derive it always like this, or you can remember it by saying that the adiabatic one has a greater slope, it is steeper. The way I remember it is, if you leave a ball here, it will roll down faster on the adiabatic one because the processes occur faster, right? That's the way, if you want, you can remember it. But the slope of adiabatic is greater than the slope of isothermal. If you talk about magnitude, again actually it's the negative, so it's slightly opposite. A couple of other small topics left. One is, we talked about equipartition of energy earlier, which says that the average energy for each molecule for each degree of freedom is half kT, right? So from this we were able to find out that the internal energy was 3 by 2 RT, 3 by 2 nRT, if n was the number of moles, right? Because 3 degrees of freedom. Actually this is not always true, and the degrees of freedom are different for different molecules. I'll not derive it for you, I'll just tell you what these are. So if you have a monoatomic gas, like one of the gases in the last column, like helium or neon, then the degrees of freedom are 3. If you have a diatomic gas, like oxygen, nitrogen, then the degrees of freedom are actually 5, and they become 7 at high temperatures. Right, so when you talk about if it's specifically given high temperatures or given that you have to consider 7, then take 7, otherwise it will always be 5. And then there are triatomic molecules, or actually this goes for polyatomic molecules as well. The degrees of freedom are 6. Right, actually they can be 6 and 8 at high temperatures. But I don't think the high temperatures are in your process. Right, so what does this mean? This means that for monoatomic gases, Cv is equal to 3 by 2R, Cp is equal to 5 by 2R, and gamma is equal to 5 by 3. Right, remember, as soon as we know say Cv, we know Cp and gamma. Right, instead of this will be 3 by 2 nRT, so 3 by 2 R is Cv. Here it will be 5 by 2 nRT. So for diatomic gases, Cv is 5 by 2R, Cp is 7 by 2R, and gamma is 7 by 5. And for triatomic gases, Cv is equal to 3R, Cp is equal to 4R, and gamma is equal to 4 by 3. Now, when we talk about air, we'll take gamma is equal to 7 by 5, that is 1.4. And that is because air mainly contains diatomic gases, namely oxygen, nitrogen, hydrogen. Right, so the gamma of air is also 7.5. The one last thing that is remaining is, we talked about the Carnot cycle in the previous lecture. So just one small step needed to look there. The Carnot cycle had the property that it had 2 hot temperatures and 2 cold temperatures. So these are 2 isotherms. Let's say this is T1 and T2. PV curve. Obviously T1 is greater than T2. Then there were 2 adiabatic curves like this. Remember, adiabatic curves are steeper than isothermal. Right, you can name all P1, V1, P2, P1, V1, P2, V2, P3, V3, P4, V4. I'm not going to do that except for T's. Now, we found out that the efficiency was 1 minus Q2 by Q1, where Q2 was the heat absorbed, Q1 was the heat, Q2 was the heat rejected, Q1 was the heat absorbed. This basically comes from W by Q1, where W is equal to Q1 minus Q2. Right, now what are Q1 and Q2? The Q1 and Q2 during these adiabats will be 0. So the only heat absorbed and rejected will be during the isothermal process. During the isothermal process, the heat absorbed will be nRT ln, let's call this A, B, C and D. So nRT ln, and it's going like this. So it will be VA by VB. Right, this will be the Q1. This will be the heat absorbed. And then heat rejected will be nRT2 ln VC by VD. Right. So the first one is Q1 and the second one is Q2. Now there are many forms of equation for the adiabatic equation. PV to the power gamma is constant and PV is equal to nRT. Also give us, if we substitute P as nRT by V, then it also gives us TV to the power gamma minus 1 is equal to constant. And if you want to eliminate V, it actually also gives us P to the power 1 minus gamma T to the power gamma is equal to constant. Right, so we look at this one. That means if you look at the adiabatic processes, VC by VB whole to the power gamma minus 1 is equal to T1 by T2. But also, if you look at this adiabat, VD by VA to the power gamma minus 1 is equal to T1 by T2. That gives us VD by VA is equal to VC by VB, or VA by VB is equal to VC by VD. That means when this whole term is equal to this whole term and these two are equal, so the ratio becomes T1 and T2. What it ultimately comes out to is that the efficiency is also equal to 1 minus T2 by T1, or it is sometimes written as 1 minus T cold by T hot. Right, so this first formula we knew directly, the second formula we derived using these particular equations we saw. So whenever you have a Carnot cycle operating between a hot temperature and a cold temperature, this will be the efficiency, and the second law of thermodynamics says that this is the maximum possible efficiency. This completes thermodynamics. Thank you.